Hi everyone. Today we're going to talk about dummy variables or coding of categorical predictors, specifically with application to multiple logistic regression. So we've already talked about dummy variables, or sometimes called indicators, somewhat before, but just as a quick reminder, dummy variables are variables that take on a value of 0 or 1, and they are used to represent or indicate the presence of an effect on some outcome. So they're a way that we can use categorical predictors in predictive models is to use these dummy variables. So for example, we've seen how a categorical predictor, such as the sex of a person being male or female, that would have two levels, for example, if that were in our data set. So we would have one dummy variable to represent whether someone's male or female or not in our data set. And so looking at an example with this, here we can look at the relationship between the sex of a person, their age and years, and whether or not they have diabetes. So here we can code as 1 if the person is male in the data set and 0 if they're female. And similarly for diabetes, actually this gets coded using a dummy variable as well. So this is our response variable, but we code it as 1 for yes and 0 for no. Okay. And again, since sex, our explanatory variable, only has two levels, we need 2 minus 1, which is one dummy variable, to represent this in our predictive model. Categorical predictors that with more than two levels will need additional dummy variables. So for example, if we had like the region where somebody was from, say if it took on values of like North America, Europe, or Africa, then we would that would be 3 levels, so we would need 2 dummy variables to represent that predictor variable in our model. Okay, so just to visually look at what this data will actually look like, we have here the sex of the person, so being male, and then this is actually sort of under the hood. What software like R does is it'll create like this indicator column where it says 1 for being male and 0 for being female. So in order to do the math behind the fitting the predictive models, we need everything as numbers. So this is how it codes these categorical columns into something that we can work with. And similarly, it'll do something with diabetes underneath as well. So for example, there's going to be a diabetes indicator column, and this would be all zeros here, looking at this. Okay, so this is actually how it looks sort of underneath the hood. But R just does all this automatically for us as it fits, say, a logistic model or even a multiple linear regression model where we have a categorical predictor. So one question we can answer is looking at this NHANES data set, the National Health and Nutrition Examination Survey, that's what it stands for. NHANES is this big longitudinal study where they measured aspects about people over the course of time. And they have recorded on people whether they have diabetes, yes or no. So that's our binary response. Their age in years, so that's a continuous predictor. And then the sex of the person, where in this data set, they are either male or female. And so we can look at modeling diabetes using the age and sex of the person in this way. And first, what we're going to do is look and see if there's a linear relationship between the log odds of diabetes and these predictors here. So what I did up here is just this CB palette, I called it, is a colorblind palette. So these are actually like different colors in R. So this is like a code representing a different color. I was just using a colorblind friendly palette. I haven't been doing that the whole semester, but I'm trying to do it more often when I can, when I remember to, because that's a little bit of extra effort that can potentially help someone understand plots well. So it's good practice to do in general when you make plots too, if you can, if you use color to try and Google what some color blind friendly colors are. So yeah, so here what we're doing is we're making an empirical logit plot using this emp logit plot2 function, which is from the stat2 data package. So if you try to run this as well, you'll need to first run library stat2 data in order to load this R package that contains the emp logit plot2 function. Then what I'm doing is not just looking at the, we've seen before how we can look at the log odds related to one continuous predictor, which age here is our continuous predictor. This emp logit plot2 function, the 2, allows us to look at the relationship between the log odds of something and a continuous predictor, but then also stratified by a categorical variable, which here is sex. So looking at this, it's a pretty cool plot. So it allows us to sort of look at the relationships of several variables at once. So here what we see is that the log odds of diabetes is certainly linearly related to a person's age in years. So as you age, your odds of having diabetes increase. That's what we see. Okay. Secondly, what we see is that males, which are represented by this dotted sort of orangish line, have a slightly higher odds of being diabetic than females, although it is quite small, but it is noticeably consistent across these points here on the plot. So that's sort of some main takeaways from this that empirical logit plot. So now we can fit this multiple logistic model where we're modeling the probability of someone being diabetic using their sex and their age in years. Okay, and then we can print the model output using the summary function from the JTools package, like we usually do, and obtain the model output here. So nothing really new about what we've done here so far. So we have a categorical predictor in the sex of the person, and then we printed it here. So here's the coefficient estimate for sex, which is 0.241. So this is an indicator for the person being male. And since this is positive, this indicates to us that the chance of a person having diabetes is higher for males compared to females, holding age constant. So again, that's because this is positive. All right. So now looking at it a different way. So if we remember back to the table that I showed, we had this column that was for the sex of the person. So that's what we just used in that logistic model. I'm showing what would happen if we included this as like a continuous predictor called male.ind for male indicator for a person being male. And I'm showing how this actually, including this continuous predictor compared to including this categorical predictor, actually gives you equivalent results, gives you the same results. So remember, here we have the coefficient estimate for this categorical predictor is 0.214, and age is 0.058. We look at the output for including just the indicator variable instead. It's the same exact numbers. And it's not rounding. It's going to be the same exact values. So everything is the same in the table by including just this ones and zeros column versus just the categorical predictor. So this is just sort of displaying how R underneath the hood is actually doing this. It's making an indicator column for us, and you end up with equivalent results as if you coded it yourself and included it as a continuous predictor. Okay, so that just shining a little bit of light on how dummy variables work, because I think there is a little bit of mystery, and it sort of all gets done automatically, so it's easy just to not think about it too much and let R do all the work. But I think it's good to understand exactly how this dummy variables or indicators variables work when we're including categorical predictors in our models. Okay. So this was the not exponentiated coefficients. I'm going to go ahead and interpret some of these model coefficient estimates as well, just for practice. So again, we need to exponentiate things prior to interpreting stuff. So we can do that ourselves by hand, or I like to use the JTools package, the summary function from it, because it has this nice exp equals true option that automatically exponentiates all the coefficient estimates for us. Okay, so from this table output here, let's start. Let's see, what do we want to do first? Let's look at the odds ratio for males versus females. Okay, so we're talking about the odds of someone having diabetes. Okay. Odds ratio for males versus females. And we'll say given age, so of the same age. Okay, so supposing someone's the same age, we get this exponentiated coefficient estimate. So I was just showing how this was the unexponentiated one, 0.058. And then, but it gives it to us in the table what that value is. So this is the this is the odds ratio. So we can say since E to the 0.058 equals that, the odds of a male having diabetes are about 1.060 times that of a female of the same age. Okay, so very slightly higher, so 6% increase in the odds. Not that much for males versus females, but that's how we interpret the odds ratio here. Okay, so the exponentiated coefficient for this binary predictor represents the odds ratio for that predictor. And that's in general how that is. Some people think the probabilities are more interpretable than the odds, and that's reasonable. So we can actually, instead of the odds ratio, we can get what's called the risk ratio. In epidemiology, they like to call this the risk ratio. It's the ratio of the probabilities. So we get the probability of diabetes for men for a given age, probability of diabetes for women of a given age, and then calculate their ratio of the two. Okay. So here, what we're going to do is first get the probability of diabetes for a male who's, say, age 0. Okay. So actually what we're going to do, I'm going to go back up. We're going to interpret it on this slide. It's a little bit easier to get on this slide with the not exponentiated estimates. So for the risk ratio, First, what we want to get is the probability of diabetes for male age 0. Okay. So how we get that is given by the odds over 1 plus the odds. Okay. So to get the odds, to this, odds of diabetes for a male age 0 is going to be given by e to the minus, so the intercept term plus, they're a male, so we include that term. So it's kind of like this times 1, the indicator for them being male, and then plus 0 times 0.058 because that's their age. Okay. And then just simplifying that out, that's going to be, let's use R. Let's see what R says that's about. Okay. R says that's about 0. Okay, this value here. All right. So the probability in general is given by the odds over 1 plus the odds. All right. And so that, again, I'm gonna use R here as my calculator. We get about this value. And there might be some differences due to rounding. So if you don't match it exactly, it's probably due to differences in rounding along the way, or it could be. So this is the probability of diabetes for a male, age 0. And then what we do, so this is not as simple as regular linear regression was. We now have to do the same thing for females. So let's do that up here. Let me copy this whole table. No, okay. I'll just copy this text. All right, and then okay, so odds of diabetes for female. Okay, so for female, the values are similar, but the indicator for them being a male is 0 instead of 1. So it'd actually be like this. All right, and then we can use R to see what this value is going to be. And okay, so different. It's lower. The odds of being diabetic are lower for females. Okay, and then we do the odds. Oh, odds over 1 plus the odds. Okay, to get the probability of having diabetes. And again, we'll use R as our calculator here. Okay. All right. And so R says this is the probability of female age 0 having diabetes. Okay. Now try and make that more readable there. Yeah, it gets a little bit smushed, but maybe, yeah, okay. Try to do that. Okay. So now to get the risk ratio, we do the probability of diabetes for males, okay, over the probability of diabetes for females. So it's sort of like it sounds. It's a ratio of the risk of diabetes here. All right, and then lastly, calculating this value in R, we get about 1.24 if we round. Okay. All right, so this 1.24 is our risk ratio here. After all that work, that took a lot of work. There's our risk ratio. Okay, so how do we interpret this? So this means, let's see, risk ratio equals 1.24 males. The probability that a male has diabetes is about 1.24 times that of a female. So that's how we interpret that. So that's it's a nice interpretable thing that's very meaningful to somebody who not necessarily from a stats background. That's more easily approachable. So we have to go through all this work to get it, but which is not simple. It's quite tedious, but we get there in the end, and then we end up with this nice interpretable number. So in other words, men have a slightly increased risk of diabetes. Oh, and it's important to add that of the same age. Okay, and you might think, oh, this is only for somebody who's age 0, because that's what we did in the calculations. And yes, that's true, but actually, this calculation will end up the same even if we changed the age, as long as we do it the same age for the same age for both of these participants, both the men and women here. So anyways, this is how we interpret a risk ratio here and get that using the output. So that was an example with a categorical predictor that has 2 levels. We can also look at when it has 3 levels. So for example, another variable in this data set is the depression status of a person. So where it can possibly be none, where someone feels depressed no days during a month, several where they feel depressed several days each month, or most days where they feel depressed most days each month. So this is sort of like an ordinal variable in that these are ordered levels, but we're just going to treat it as categorical. We're going to ignore the ordering in this for now because we're looking at just the logistic model. Although there are more complicated models that can handle ordinal data like this, but we're not worrying about that for the moment. We're also going to use the person's age in years and whether or not someone, and then we're going to model whether or not someone has diabetes still. So again, like I mentioned before, we have L-1 dummy variables for our categorical predictor, where L is the number of unique levels. So here, 3 unique levels means 2 dummy or indicator variables. Okay, and looking at it again, just to give a better picture about what this is meaning. So if we manually coded these ourselves, here's just our 1 categorical predictor column. but it has sort of two implied dummy columns with it. We have like an indicator for feeling depressed several days each month, and then an indicator for feeling depressed most days each month. Okay. So this is again how R fits these classification models underneath the hood. It creates these indicator columns to represent this categorical predictor. And then we're modeling again this diabetes status. So if we had the indicator column in here for as well for the diabetes column, it would be 1 for yes, and then 0, 0, 0, 0 for the no's. So looking at this example, now we can look at, we're interested in if depression status is related to someone having diabetes. So this is a good time to mention we are not answering a question about causality. So we are not concluding if depression causes diabetes or if diabetes causes depression. We are just looking at the association in this data set. So we can't make causal conclusions from this. But certainly exploring the data and looking at associations in the data is a good place to start if you're interested in answering clinically relevant questions like this. So, just something to mention. We're not proving causality. So looking at an empirical logit plot like we did before, we look at the relationship between age and the log odds of having diabetes. We see again, age for all the depression statuses is still linearly related to the log odds of having diabetes. What we notice is that the group who feels depressed most days each month has the highest chance of being diabetic, followed by the group that feels depressed several days each month, and then the least likely to have diabetes is the group that feels depressed no days each month. Okay, and again, we cannot conclude causal relationships here. We're just looking at the associations in the data. Okay. One thing to note from this plot is that if these lines did not have the same slope, these three lines, if they crossed, that would imply an interaction between depression status and age in years. So if these lines were not parallel, we should consider an interaction term between age and depression status in our model. But because these lines are parallel here, we're not going to bother including an interaction term as well. So that's just something to note, that these empirical logit plots can tell us a lot about our model and potential predictors to include. Okay, so now fitting the model and looking at the output, we see that we get our coefficient estimates for the effect of someone feeling depressed several days each month or most days each month, and then their age in years. So this was again using the categorical variable depressed. So if we look back at the table and see how that was coded, it's just a string variable, they say. It's just words. But R is able to fit a regression model with this as a predictor and get these estimates. Okay. Now if we look at using the indicator variables as just separate predictors in our model, where they're all just continuous predictors here, we actually get the same exact output again. So just like before, with using the sex of a person, we could use an indicator variable instead of that character predictor variable, and we get the same result. So 0.394 is the estimate for several, 0.952 for most, and if we look, those are the same values as when R used the string variable as its categorical predictor. So Again, this is just showing the equivalence of those two views of the data and how R is actually recoding things as zeros and ones underneath when it fits these logistic regression models. So a good thing to understand again about how this is working. So just like before, I'm going to exponentiate the estimates to facilitate easier interpretations for these things. So one thing we can look at here, there's a lot of things to interpret. Let's see. So we can look at the odds of someone having diabetes if they feel depressed several days of each month versus someone who feels depressed no days each month. So I'll show you what I mean here. So interpreting this coefficient estimate here, since E the data hat for several equals 1.483 because it's already exponentiated for us here. Oops. Let's see, goes like there. The odds of someone having diabetes who is depressed several days each month is about 1.483 times that of someone who never was depressed, holding age constant. So for only for people of the same age. Okay. So their odds of having diabetes is about 1.5 times that of someone who never feels depressed of the same age. Okay, so there's somewhat of an association between depression status and people having diabetes in this data set. And notice that I did this interpretation was relative to someone who never feels depressed. And so that's because this none category for the depression status variable is our reference or baseline category here. So it doesn't have a predictor in this model, a coefficient estimate in this model output, and that's because it's the baseline category. So interpretations of these other estimates are just relative to the baseline category. So this sort of gets at like how if we think about how the data is coded, we have this indicator variable for several, indicator variable for most, but we don't have an indicator variable for none. So this gets absorbed. Sometimes people say it gets like absorbed into the intercept term. So if we interpret the intercept term here, I'll show you what I mean. So since e to the intercept term equals 0.006, the odds of someone who never feels depressed, odds of someone who never feels depressed and is 0 years old, so a little bit of a weird having diabetes is about 0.006. Okay. This isn't necessarily the most sensible thing here. It's like technically, yeah, I don't know if it's possible for someone who's 0 years old, a newborn, to have diabetes or not. But this is how the intercept term is interpreted here. So it's the odds of someone who has their predictor variables all 0 having the outcome of interest. So in this case, odds of someone age 0 who never feels depressed, that's the reference category. So when these are 0, and yeah, that's very small here. So very unlikely, which is sensible. That makes sense here that a newborn's not very likely to have diabetes at all. Yeah, so that's how we interpret coefficient estimates for categorical predictors for multiple logistic regression. So thanks, and we'll see you guys next time.